So welcome back, everyone, so far. We're just running the clock at the moment before we get started. Well, looks like it's official. Excuse me. Welcome back, folks. I think the cold air is just bothering my throat. I won't take up your time too long today. I know it's snowing quite a lot, but our goal today is to finish off chapter 13 and connect it to chapter 14, our first look into inferential statistics. But before we discuss any of that, any questions that folks have to start us out today? Okay, as far as the exam grading goes, I should be having these completely graded sometime in the middle of the weekend. As soon as I have them graded, I'll be posting the grades up into the Moodle, and the hard copies I'll have available in Tuesday's class. For people who took their exams in the testing centers, I'll have your exams emailed right back to you. And just out of a safe sense of fairness, if you took the exam in class in person and you just want to look at it earlier, don't hesitate to email. I'll be happy to scan it and send it to you. But for the moment, we're going to get into finishing off chapter 13, taking another look at that central limit theorem. And maybe another thing to emphasize about chapter 14, where it says introduction to, that's a pretty strong emphasis. Think of chapter 14 as it's going to contain a couple methods that we won't use throughout the entire book. We're going to replace them in chapter 17 when we get into the t-distribution. But the purpose of chapter 14 is just to get a really close look at what do we mean exactly by a confidence interval? What do we really mean by a hypothesis test? So we'll be looking into those things before we go into our more firmly applicable procedures with the t-distribution. But for the moment, we're going back to chapter 13. And here's where we left off right here, the good old central limit theorem. There's lots of comments I have about this. One comment was that we had another theorem that looks oddly similar, but it has an assumption that you're sampling from a normally distributed population. Unfortunately, it's just not exactly applicable in the real world. Plenty of populations we want to study are heavily skewed. But this theorem is applicable even to the skewed populations that could have a whole bunch of pathologies going along with them. The idea is, if you have a large enough sample size, then even with the underlying population being badly non-normal, X bar is still going to be approximately distributed in this way. But the trick for the next part of the notes is to determine what do we mean by large enough? In calculus, sometimes you have to quantify those by using epsilon and delta type arguments, because this really is an actual type of limit we're thinking about. But we're not trying to get into the nitty-gritty details, so I have just a couple, well, one rule of thumb to go along with that. So for what's considered to be large enough, a big rule of thumb that's used is this one right here. But it is really just a rule of thumb. We have to keep in mind, oftentimes if your sample size is at 30 or larger than 30, you're in a pretty good place. The author that mentioned this came from an engineering textbook, says, however, there are populations for which even a sample size of 40, sample size of 50 does not suffice, but they are rarely encountered in practice. Well, I looked into that. I tried to find a situation where sample size is 40, 50 doesn't work. And that's what the next example is all about. Any questions first, folks, with this statement here about the central limit theorem? Okay, so here's a weird example where the rule of thumb just is absolutely not going to work. This was done through a simulation, but it's still a pretty realistic situation that could happen out in the real world. It says here for this example, and this one came from the Statistics for Life Sciences. I think we've cited this text twice now. What's going on in this experiment is we're using the central limit theorem, but we're deciding At what sample size is the central limit theorem actually being effective? First, let's look into what the experiment was here. This was an actual psychology experiment, so these are always a little bit weird. It says, a psychologist measured the time required for a person to reach up from a fixed position, operate a push button with his or her forefinger. So that's the whole experiment. But this is psychology experiment, so you know there's always more going on. If you've ever been a member of a psychology experiment on campus, they always have to debrief you to tell you what the study was really about versus what you thought it was about. There's always a big mismatch. So what's going on here is they say the distribution of time scores, these are measured in milliseconds, for a single person, again, just sitting down, reaching up and hitting a button, that's it, is repeated by the density curve shown below. So here's that density curve. The mean of all their values, we're going to think of the entire set of values as now being a population. So we're using a parameter mu there, is right about this location, even though the peak is way out here. That's just due to the right skew. It says about 10% of the time, the subject fumbled or missed the button on the first thrust, and the resulting delayed time appears as the second peak of the distribution. So probably what was happening in this experiment was they might have been told, we're just going to see how fast you can do it. So now the person doing this experiment, the subject, has got maybe a little bit psyched out in their head. The first time they go to hit the button, they miss, or they just get psyched out. They're not doing this in a natural way. And that's what happened over here. It says next, because of the two peaks, the overall distribution is, I like this word, this is their language, violently skewed, and I would agree with them on that. It's strong language to match the skew we see here. The population mean for this was 148 milliseconds, but due to the large skew, the standard deviation is 105 milliseconds. So nonetheless, even though this is one of the really bad distributions that could come up from an experiment, central limit theorem still applies, even in this case, of violent skew. So below, what we're doing is imagining we took repeated samples from this as a population, what the sampling distribution of X bar would be. Central limit theorem says it ought to be normal, the way the sample mean X bar is distributed. I think they use Y bar in this textbook, so think of that as synonymous. Well, there's the Y bar. It says the figure below shows the sampling distribution for Y bar for samples of various sizes from the time score distribution. So this is how the population is distributed. And if you take samples of size 4 from that population, calculate the mean, and then do this over and over and over again, you get this as the sampling distribution. What they did was they ran this through a simulation, obtained a histogram, and just found a nice smooth curve that modeled the actual peaks in the histogram. It's still very skewed, but if you double the sample size to 8, this picture emerges. Somehow, some way, with a larger sample size, it becomes more symmetric, even with the underlying population being as badly awful as it is here. That's what's being expressed when we say the sampling distribution of X bar is approximately this for large enough values of n. Well, that's not really normally distributed over here, but the sample size n is just 8 on that one. Let me zoom in a little bit more. So if we increase the sample size, here's the next situation. At sample size 16, still not really a great normal curve. And here's where the rule of thumb mentioned in the previous textbook came in. At sample size 32, it's starting to actually look normal. Now we just would have to decide, is this normal enough? There's still skew to the right, and there always will be. What the central limit theorem is saying is, as n goes to infinity, the distribution, let me say this in a more complete way and hide those slides there. The sampling distribution of X bar converges to a normal distribution centered at the true mean mu, standard deviation sigma over the root of n. So really the central limit theorem is a statement about limits altogether, a limit with a probability distribution. So as n gets larger, we should see the shapes of these get closer and closer to n, the normal distribution. And we can make it as close to the normal distribution as we want by just selecting a sufficiently large size of n. But we have to keep in mind that samples are expensive too. So there's another constraint. We can't just say we want sample size 1,000. That might be just cost prohibitive. So a sample size 64, this would probably be a great approximation through the normal distribution. Sample size 128, if we could afford it, depending on how we're being funded, that would be even better, but still just a touch of skew to the right from the original population. So again, that's all the central limit theorem is really trying to say. It's a pretty wild expression because there's no reason to assume the sample mean of X bar, the sampling distribution of X bar should approach normality exactly, but it really does through the limit. It's a tough theorem to prove, but if you're interested in that kind of stuff, loads of real analysis and probability would be the starting point for getting into how in the world to prove that kind of theorem. But any questions, folks, with just seeing it for a third time through this kind of graphs? Okay, well, last thing we're going to do on these notes is just do a couple computations where we actually use the central limit theorem for a second time. The homework set in chapter 13 is a little bit short because this is a pretty technical chapter. Really, our main goal of chapter 13 is just to get the qualitative feel through these kinds of pictures of what the central limit theorem is really trying to say. That's probably the more important thing, but it's also important to know how to calculate through it. So here's our next example. These examples are weird, I have to say right away. We mentioned before in the last problem, a lot of times when you're using the central limit theorem, you're doing a type of what if analysis. And that's what's going on in this problem right here. They haven't even collected all their data, but they know a simple random sample of size 10 is going to be gathered. And the head researchers of this problem are just wondering, by use of that theorem, what could happen when they go to gather that sample. But let's read the context in full and see exactly what's going on. Starts off by saying scientists at the Hopkins Memorial Forest in Western Massachusetts have been collecting meteorological and environmental data in the forest for more than 100 years. So they have really great data. But keep in mind, 100 years of data doesn't mean you know exactly what's going on in the population, because populations change with time. So something could change quite a lot from one year to the next, and it's as if you have no data. They go on to say, in the past few years, sulfate content in water samples from Birch Brook has averaged 7.48 milligrams per liter. So this is historical data, but we're going to eventually model the sampling distribution through this kind of data here. So we're going to assume that mu takes on this value, 7.48 milligrams per liter. We're not necessarily saying we know that value to be exactly. We're saying if this is accurate, what could happen when we go to take a sample of size 10? It also says we have a standard deviation, but let me first grab that. Notice that they said average. We just have to know average and mean are synonymous when it comes up. And we next have a standard deviation, 1.6 liters per milliliter for sulfate content in that brook. So that gives us a value next of sigma equals 1.60 milligrams per liter. So we'll assume the population of sulfate content can be well modeled by a normal distribution using these parameters. So that's the big assumption. What that assumption is saying, or really admitting, is that we don't really know those values. We're just going to say, if we assume that these values are accurate, it came from a good place, it's from data. What can happen when we go to gather this sample? So this is the what if analysis going on this problem. And again, it's weird. They haven't even gathered the sample. They're just using old data here from the past few years to try to model the population through those parameters. Well, the first question is always the most confusing with these kind of problems. In chapter 11, the confusing question was, what is the probability distribution of some variable? And this one is asking for the approximate sampling distribution of the mean. Because it said sampling distribution, that's a giveaway that we're talking about the central limit theorem, because the central limit theorem provides the sampling distribution of X bar. So when you see this, think central limit theorem. So really all we have to do to answer this question in full is to say that X bar is distributed as, they ask for the approximate distribution, so we could say approximately to the n, just to be extra careful. I don't have a symbol for approximately distributed as, unfortunately. They said assume normal. We'll use the parameters that have been estimated. We don't know their exact figure, but 7.48 would go here. Then 1.60 going in for sigma in this location, and I filled in mu in that spot there. We're divided by the square root of the sample size. But when it said a random sample of size 10, a simple random sample, even better, that means we have sample n equals 10 when we're throwing into the formula up here. And that's the exact distribution. It's your call if you want to estimate this part right here, but I think it's better to just leave it exactly as that. We'll import these figures into RStudio and just make RStudio do all the final approximations. Better not to round in the middle right here before doing that step. But if you did round there, go for several decimal places for extra accuracy. It is a standard deviation, so it's very sensitive to rounding. Well, that's part A done. Any questions at all, folks, getting through this portion here? Okay, so part A just forces us to use the central limit theorem, but it's good to have a part A in this kind of problem because it's also a good way to grade by partial credit. If you made a mistake here, I would know what your model is, and I would know how you got those numbers there. So even if your probability is wrong, but I know what the values are, and you're getting the right numbers based off those values, I'd be able to assign partial credit for the next responses. And by the way, the next response says, what is the probability that the mean, from that already, we want to write down probability, X bar will go right there, only because they're asking for the probability of the mean, the sample's mean. So X bar is in the middle. We want to know what the probability that the mean of these 10 measurements will fall between those two values, 6.49 less than X bar. Let me just start off with that. Didn't think far enough ahead on that. 6.49 less than X bar less than 8.47. So we want to come up now with that probability there. So again, this is why this is a what if analysis. Historical data says mu should be this value, sigma should be this value, and these two values, 6.49, 8.47, are not too far off of this figure. So if this probability is, say, really, really high, that gives the researchers in charge of this study some sets of expectations. So imagine this comes out as a high probability, say 0.95, something like that. But then they went to do the study, gathered their sample of size 10, and maybe X bar is larger than 8.47. Maybe it's 9, or maybe it comes out as a 5. That would be really weird if this is at high probability. It would tell us two things must have happened. Either the values up here are wrong, or if they're accurate, maybe the sample was not gathered in an appropriate way. Something could be wrong with the sample itself. Or maybe it was just really a weird sample. Sometimes rare events do in fact happen, so we have to accept that possibility as well. But at least when you run through this kind of computation, even before any data has been touched, this gives you a set of expectations. So that's the what if analysis that we've been mentioning. It's a weird problem because we don't even know the sample data. But we can say what should happen with the sample data if our model is accurate. Well, let's do the computation. It's similar to the ones we've done before. First thing we want to do is take a look at the model, input the values. Usually I'm looking right around here when I'm starting off. Let's go. Mu gets 7.48. Sigma gets, I usually abbreviate to sig because sigma is a function, and usually it's not a good idea to make that a variable. So sig is 1.60. Also, I like to also give it the sample size. We mentioned in class the other day, though, that is kind of optional in your syntax. You can just write in the divide by root 10 as well, and it'll all come out just as well. But I'll throw in the sample size 10 here, just to keep that pattern from before. And here is, excuse me, part B. Because our variable x bar is in the middle, we have to hit p norm twice. Once on the upper value, then call it again on the lower value. So it'll become p norm 8.47, and then pass the parameters, mu, sigma. But always kind of look over here as well, because we're using the central limit theorem. You have to take sigma, divide by the square root of sample size n. So that's going to be the first run. And if you wanted to, just to save some time, make this all accurate, you could just copy this whole thing, come over here, paste it. I hit enter so we can see it all in one page. I'm running out of the horizontal space. Then just move over here and update to 6.49. So this is going to give us the probability that the sample mean is between those two figures. Running the whole thing, we have probability to 4 decimal places of 0.9496. What we did, folks, that's the probability calculated through the central limit theorem once we got that sampling distribution. It is an approximation. You know, I forgot to say that here. X bar is distributed that way approximately. Because that's an approximation for the distribution here, this is also an approximation as well. So if you really want to emphasize that, you could say approximately that probability, but no harm if you left it like that. Well, any questions at all? Oh, I got a couple chats. Hayes says, can you tell me why I'm getting a different value? Yeah, absolutely. So you've got p norm mu sigma divided by square root n minus p norm 6.49 mu sigma divided by square root of n. It might have something to do, what is that? Please cannot be set. Oh, good eye. I didn't see that at all. So from class, Alexis says the thing that's missing is the square root right here for your n is what's causing the difference. That was really hard for me to see on that syntax. Thanks for putting it in the chat. That's actually kind of a fun way for us to all kind of brainstorm to see what could be missing on the syntax. So I really encourage anyone to try that out as well. Other questions so far? Still don't know what I did wrong on this. That was a minus right here. Yeah, I was running out of horizontal space, so I took what it would look like this and just dropped it down a line. Other questions so far? Okay, so the head researchers in charge of what's going on with Birch Brook, looks like they measure this every year, and they've been doing it for hundreds of years. They now know that before they even gather any data whatsoever, the sample mean should be between those figures with a really high percentage chance of almost 95%. Again, there's a 5% chance, 1 in 20, X bar is away from these values. But now that they have this set of expectations, if X bar came out at, say, like 20 milligrams per liter instead of 8.47, that would be so wildly off with what we're seeing here. Something is potentially wrong with either the sample, the parameters, or maybe something else could go wrong. So that's what part C is all about. If this is really an accurate thing or computation here, that probability, we do need to have some assumptions working in the background. Anyone see what some assumptions should be? It says mention at least 2, but you know, there's really several that you could say. I'd say there's several you can mention, but there's one really big one. I'll go first. This isn't the big one, so if you have it in the back of your mind, feel free to shout it out. But for this probability computation to be accurate, one assumption that we really have to have is that sample really has to be a simple random sample. If for some reason maybe the students went out to gather the sample or some lab assistants went out and they were just short on time, sometimes people just go and take the most convenient sample possible. Maybe just go right by where the parking lot is, grab some samples and call that good. But that wouldn't be a simple random sample whatsoever for something like this. So assumption one would be we must have a simple random sample. So that's definitely one assumption that has to hold. Anyone say any others that must hold? Kind of tricky in a way, right? Well, oh, we've got a chat. Cameron says, is it that the data is normally distributed? Good call, Cameron. To me, that was the big one. We could add another response to say the parameters must be assumed to be highly accurate for that probability to be accurate. But I think of that as being the bigger one that you just mentioned. How is the actual population really distributed? Our sample size is small, right? So if our population is bad, like say this one, and we're sampling at around size 16 or 10, that might not give us an accurate normal probability computation at all. This is actually severely skewed still. That would have been better at size 32. So that's the big thing that's going on with this one. We don't really have any indication anywhere in this problem how the population is distributed, how badly skewed it is. So let's say it the way you said. Let me pull up the chat again. We need to know if the data is normally distributed and let me add just a little more. We need to know if it's normally distributed since the sample size n is small. So there's no guarantee here that the central limit theorem is just going to work at any sample size. That's something we really have to look into. They have hundreds of years of data, and they were calculating and estimating these values from recent data. So all we have to ask them is, hey, can you give me a histogram for the recent samples that you have taken so we can see how close or how far away from normality we really are? Then we can assess if the sample size 10 is appropriate at that point. But without that information, this is up in the air if it's accurate or not. Even if those values are very close, who knows if we don't know how badly the population itself is distributed. So that's the downside of the central limit theorem. Low sample sizes have no guarantee to work out unless you really know underlying population is highly symmetric, mound-shaped, much like a normal distribution. But for part D, we're going to turn this around and find out what values A and B we need to find to get this probability here, 0.99. Then we'll give a practical interpretation of the interval AB after we find it. Any questions first, folks, with part C, or anything that you'd like to add? Okay, let's get part D a try. Oh, we got a chat. We'll go over. How do we find part D based on B? Let me take a look. Well, I would say part D really isn't based on part B. Really, the only thing that changed was we didn't have a probability here. We had to actually compute it, but they gave us the values that X bar range from 6.49 to 8.47. So part D switches it all around. It supplies the probability 0.99, And now it's our job to find what values A and B is going to give that probability there. So really what's going on with these two problems is on this one, we had to use p-norm to find that probability. But if we want to find the A and the B, we have to use q-norm. Does that make sense so far? Yep, absolutely. Okay, now looking at this problem a little bit more carefully, some people might feel like there is something kind of missing in the wording here. If that's you, good on you. It's not a fully precise statement here. Probability X bars between A and B. We know there's multiple A's and B's that can make that work. But what makes this a unique answer is one extra thing. Let me put it here. If this question would ever come up as, say, a homework question or exam question, I would have to be very specific. We're looking for central probability here. So in other words, we're going to keep our X bar, thinking of that as going to be the center, and just move off a distance away from X bar to the left, away from X bar to the right, where the center is exactly 7.48. So central probability there means that's the center we're using. And you could change your center to something else and find other A values and B values that could give you still the same probability. So to just make it a more specific problem, that has to be baked into the problem a little bit. Maybe another visualization, just a really quick one. If you have a probability like this, and central probability 0.99 is from here to here, you could still get probability 0.99 just by moving the right distances to the left here, and maybe a slightly, I didn't mean for those to be linked, but you can move things around just right. Say maybe you move this, oh dear, say you move that way over here, and then just make the right adjustment to put it here to still get probability 0.99. So that could work out, but not really in the spirit of the question. To be specific, you would have to say it this way, central probability. So going after that central probability, not as tricky actually in WebAssign, getting the eraser going is. All we have to now do is use q-norm twice. So we'll write out back into RStudio, part D. Maybe before we go to use q-norm twice, let's put down an extra graph just to kind of organize this. So we need some extra space, I'm thinking. Curve going this way. This is a probability of 0.99 that we're working with. And in the center, 7.48. So we're looking for an A value here, a B value about here. To change a heart on the color there. Let me change this to something else. So constrained between A and B, imagine that's perfectly symmetric. Maybe if I draw it different, sort of looks that way. In the middle, we have 0.99. And so now, to get this region, the thought is its area would be equal to 1 minus 0.99 divided by 2. And same for this area here, 1 minus 0.99 divide by 2. That's only because we're looking for exactly central probability. This value here would be symmetric, same value of the area here as well. So that informs what we should write out in our syntax. Let's go for the A value first. We're going to use the q-norm function and go q-norm. Areas are probabilities, so we can just write in, this is really a 0.01 divided by 2. But if you're in the habit of being super careful, no harm in going 1 minus 0.99 halves. Now it's RStudio's problem to take care of that. We still pass the original parameters like we did over here, mu and sigma divided by square root of n. So there are those. And let me actually name it so we have something. Well, actually, we can just leave it like that, I suppose. First number that comes out, 6.17, and that would be the A value for this interval so far. Is that looking all right to folks at the moment? Okay, so this is sulfite content, and I forget the unit already, milligrams per liter. So I think probably an appropriate rounding on this might be about 6.18 milligrams of sulfate per liter of the Birch Brook. Let's one figure down. Once we get B, we're on our way. So for the B value, we go Q norm again, 1 minus 0.99. Halves mu sigma squared to the n. And now there's lots of things you could do here. You could use the complement rule or just control the direction here. Our area is on the right tail, so we set lower dot tail false, and we'll be using right tail area to get B. So let me hit comment there, lower dot tail equals false. Now let's take a look at this in the results. We have 6.17 from this first part of Q norm. When we ran Q norm again with lower dot tail set to false, it came out to 8.73. Looks like that's a plausible value for B. And notice it's a little bit bigger than what we got over here, which seems about right because this one's at probability about 0.95, and we're doing probability 0.99. So the interval should be wider at a higher probability. And that's what we're seeing with a larger value of B and a smaller value of A, from 6.49 to smaller 6.17. But let me record the result. B is 8.78 milligrams per liter. But we've got the interval from A to B. Now all we need is the practical interpretation using context. That's just writing a bunch of things down, remembering what X bar was meant to represent and that kind of stuff. This is probably the harder part, getting those two values. Any questions at all finding those? Okay, now for the practical interpretation next. Let's say here, just to organize what's going on, if you came back to these notes, this continues. If we're going to give a practical interpretation to any probability statement, they all can go basically the same sort of way. We could start by saying there is a 99% chance but that's just a personal choice. You could say with probability 0.99, and that's completely fine as well. We'll say there's a 99% chance that it's a probability statement about the sample mean that hasn't even been computed yet. So again, it's a what if analysis. We'll say that the mean of the sample we should mention the sample size as well, because that's very important in this probability. Notice in RStudio that n changes, all your probabilities change. Imagine they took a sample size at 100, then Control Enter. Oh, I guess I had it running. The new values would be way off what we saw over here at a different sample size. So we should mention the sample size as well. Sample size of 10 observations from Birch Brook. I believe that was the name of the stream we were looking into. Let me reconvene and see if I've got these thoughts in line. So 99% chance. The mean of the sample from 10 observations from Birch Brook is between those two values. But it comes with a unit, so you'd have to say what this is exactly. This is sulfite content, so let's bake that into the problem as well. So we'll say that the sample mean of the 10 observations for Birch Brook has a sulfate content between 6.18 milligrams per liter and 8.78 milligrams per liter. At this point, we've solved the problem entirely. That's the practical interpretation for those two values. Again, this altogether is just a strange what-if analysis. We were wondering, what's the probability that what values would you get if we're talking about a 99% chance your sample mean is constrained between these central values? So if they go and get that sample and it's lower than this or bigger than this, something weird has happened. Something wrong could be with the model. We looked into things that we need to have. One of those things could have gone wrong. Maybe one of the parameters is off here. Either one could cause a problem. But again, gives us a set of expectations. And it's always interesting when those expectations are not met. Maybe what it means is the population really has changed in the current year for Birch Brook. New processes are happening. That kind of stuff could be what's going on. But that's the end of the central limit theorem problem or chapter. Really, it's kind of interesting to do these what-if analyses, but this is not the major use of the central limit theorem. What the central limit theorem is going to allow us to do, starting in chapter 14, but more thoroughly in chapter 17, is really do inferential statistics. And in inferential statistics, we don't actually want X bar in the middle there. We go and calculate X bar. We know its value. We want to put the parameter in there, mu itself, and see what will the central limit theorem say if we can put a parameter in the middle, mu. So that's chapter 14. We're going to take a look into it right away. But any last questions or thoughts before we close out this chapter? Okay, let's give it a try. We got through all the kind of review from statistics type of concepts that we need to get through. Chapter 14 is still a kind of introduction, but we're getting into the main target, the main objective for our course, the actual statistical methods. So let's load up chapter 14. And it starts off with the central limit theorem again, because again, it's really the major thing that's going to rescue us and allow us to actually do inferential statistics. It says, if we gather a simple random sample of size n from any population, when we know that it has a mean of mu would go there. When we know the population has a standard deviation of sigma, it would go there. And here we are going to say right away, in this chapter, mu is unknown. It's always been unknown, and even in the prior chapter, we were assuming certain values for it to just say what could happen if mu is equal to this or it's equal to that. But here, we're not even doing that. We're leaving mu fully as a complete unknown. We're not going to put in a value to it. Our job is to estimate it this time. And keep in mind, we emphasize this is really just an introductory chapter to get us starting to think about inferential statistics. Because it's an introductory chapter, our author says, here are the simple conditions we're going to assume throughout this chapter. That we have a simple random sample each time we're looking into the problem. That's pretty standard. Oftentimes we try to get away with this in statistics, but it takes a lot of work. Sometimes you might read a study that says, we have a representative sample of people with this genetic disorder, something like that. That's a little sketchy. It means they don't necessarily say it was random. They just think their sample represents the underlying population. That's working really hard in statistics, and lots can go wrong. So that's a reasonable assumption to get away from all that problems with that kind of issue. This is a different problem. The variable we measure has a perfectly normal distribution. We're saying the population is normally distributed every single time in chapter 14. That's really just a mathematical fiction, but it's actually okay because the central limit theorem doesn't care. Your sample size can be large enough to take away this assumption of normality in the population. We just mentioned, we don't know the population mean mu, so it's reiterated here. Here's the weird one. That deserves a warning practically, but we do know the population standard deviation sigma. This is how statistics was done historically. They didn't actually know sigma, they just guessed. They put in a value and they ran with it. How did they guess? Back in the day, before the t-distribution was discovered by Gossett, they estimated sigma approximately equal to the sample's standard deviation. And that seems about right. It is the right estimate to make, but there is an error in that estimate as well. If we can't quantify or describe that error, then the procedure that they used historically was flawed. However, there are some rare cases where you do know the value of sigma. For example, one off the top of my head is intelligence quotient scores, IQ scores. Those tests are standardized for the purpose of making the standard deviation. I believe it's 10 or 15, I actually forgot. But that's one case where you would know the exact value for sigma. So those are our assumptions. Mu is an unknown, but we're going to assume a known value for sigma. In chapter 17, we're going to take off that concerning assumption. But for the moment, we'll just go with it to just get a first look at these procedures. So here's how example 1 goes. It says, consider a population, the unknown population mean mu, a known population standard deviation sigma, and further assume the population is distributed normally. So we have everything we were mentioning up here, just a really nice situation. We want to estimate mu, and we've done that a lot. We take a sample, we calculate the sample mean x bar, and we make that estimate right there. But we've made big complaints about that really since the very start of class. That estimate is useless until we quantify the error in that estimate. And so that's what we're going to do right now. Approximate the error in making that estimate anytime you make that estimate under these conditions as well. Well, one way to start is, let's pause right here for the moment. Go back to chapter 11. I know it's ways back, it feels like. But we need one visual from this chapter here. The one graph we didn't pay a lot of attention to, we just kind of put it here in the middle, just to say this is another way to look at the normal distribution through the so-called empirical rule, or 6-8-95-99.7 rule. It tells us that approximately 95% of the area under the normal curve would be within 2 standard deviations. That's a very pixelated -2, +2. So 2 standard deviations of the mean, which would be mu in that problem. So let's take a really quick screenshot of that line right there. I'm going to just temporarily throw it into the notes. Actually, we could just leave it on the bottom of the notes, just as a quick reference to coming back to here. And to approximate the error, we're going to use this approximate statement. 95% of the area under the normal curve is within 2 standard deviations. But it's not this normal curve, so we have to do one other thing first. First, we'll say, by the central limit theorem, we have that the sampling distribution of x bar is distributed as, now in practice, this is an approximation, but they said the population is distributed normally, so this would be exactly normally distributed here. So we'll go n for normally distributed. The mean here from the population would go in to that location. Sigma from the underlying population goes in. We're drawing a sample size of n, so we divide by the square root of n. And that's just the central limit theorem that we've been working on in chapter 13. So now when it says 2 standard deviations from the mean, these are the standard deviations being referred to. And when it says of the mean, it's referring to this. So that's the mean being referred to. This is the standard deviation being referred to down there. And now we can just write down an equation that captures all this. So being within 2 standard deviations of something could be along these lines. Probability that the absolute value of the mean toward away from 2 standard deviations. So I'm writing down the distance between the statistic X bar and the mean is going to be within. Within implies a less than. You could go less than or equals, you get the same probability statement. 2 standard deviations means 2 times sigma over the root of n. This is going to be approximately 0.95. The way to make this more accurate is that 2 there just has to be a slightly different figure, but we'll go with approximate just to get a feel for how are we going to put the parameter mu in the middle? Well, it's already in the picture through this statement down here. So it reads out the probability that X bar is within 2 standard deviations of the mean is approximately 0.95. So we've used up the empirical rule. Now we can do a bit of a rearrangement here and express this entire inequality in a slightly different way. But any questions so far, folks, with using the central limit theorem and the empirical rule? Okay, now let's work with the inequality in the middle. So we can say next, if you take this entire inequality statement, X bar minus mu less 2 sigma over the square root of n. So let's give that a special color because that's the big thing we're trying to emphasize. You can take off these absolute values and now just convert this into a triple-sided inequality. This will imply that take this quantity, make it negative 2 sigma over the root of n would be less than, we just state what's in the absolute value, X bar minus mu less, then just restate this, but with a positive sign in front, 2 sigma over root n. I said that in a weird way. A positive sign in front means no sign in front, really. So that's our new statement. Equivalent to the one above, which means we're not changing the set inside the probability set function, we're just rearranging it. And we can do even more rearrangements to this. Let's multiply all sides by -1. Why not? You can do that, and that gets mu closer to being solved. So multiply all sides by -1, and we'll get 2 sigma over root n. We're multiplying by a negative sign, so the trickery with algebra is these change their directionalities. Multiplying by -1 here would give us minus X bar plus mu. Direction change here, greater than, multiply by -1, -2 sigma over the root n. This is kind of awkward to look at, so I'm going to read this out again, just changing the order. That's a good step to skip from here to here, but it's kind of hard to see if we did that skip. Usually when you multiply an inequality like this by -1, what you really do is you take that, make it negative, you -2 sigma over root n, you still say less than, you multiply this by your negatives, negative X bar, now positive mu, keep the same directionality less than, multiply this by -1, and you get 2 sigma over root n. But that's just equivalent to doing it this way, and then just reading this out, writing it in that same corresponding way. So I just really rewrote this going right to left. Does that make sense to folks so far? That means we're just about there, right? Mu is solved in the middle the moment you add X bar to both sides. Well, all 3 sides, we should say. There's 3 sides now to this. So last steps. We now have that X bar minus 2 sigma over the root of n is less than mu, which is less than X bar plus 2 sigma. That's a terrible sigma. Let me fix that. 2 sigma over the root of n. And now we have mu in the middle here. We can now say, therefore, probability. This is a lot to write in. This is a more compact statement for sure, but this is what we're obtaining. Forgot the bar on this one, don't forget that. the probability that x bar minus 2 sigma over root n is less than mu, that's the unknown in the middle, is less than x bar plus 2 sigma over root n is approximately 0.95. And then we say from this, x bar plus or minus 2 times sigma over root of n is an approximate because we used an approximation right here, is an approximate what we'll call 95% confidence interval. So we had a task, and what we got was a confidence interval. Recall what we really want to say is, what is the error in this estimate? But the moment we got this interval, we can see the error. It's going to be right here. So this is the margin of error, is how we like to call it, of error in making the estimate from right over here, that mu is approximately equal to x bar. So we now have something really big. We got it through the central limit theorem. And that 2 there, it's an approximate value, but we can make that even more precise and take off this approximate statement right here. So we basically have the full procedure. This is not a problem that I'm going to ask you to do over and over again. That's why, well, I did call it example 1. Usually I say just example if it's not going to be a real homework problem, but I apparently forgot on this one. Actually, let's just leave it that way, just to emphasize. But the purpose of this problem was really to just see how the central limit theorem works in the background, to get us down to the interval, and to really emphasize that that's now a good estimate because we have the error in that estimate. Twice the standard deviation divided by the square root of the sample size. Notice that the error is then going to shrink as the sample size goes higher and higher and higher. That's a great feature to have in your problem as well. Well, any last questions, folks, on looking at this kind of analysis? Okay, we pretty much have a confidence interval then. All we need to do is be a little bit more accurate with this 2 right here. We're going to later call it, well, very soon, we're going to call it a critical number. So that's going to be our next goal. I'll leave this statement right here since we had to use that in order to get this whole inequality stuff working for us. And now, let's put a little break here. Oh, and there goes the break. Here's our next concept, the critical value Z star. Again, we kind of estimated Z star when we put a value right here through this rule. So Z star wasn't exactly 2. It turns out it's 1.9600. And the way we calculated it is in this way. The critical value Z star just counts number of standard deviations. And that's what this theorem was, or this empirical rule was doing up here, just counting number of standard deviations. We just want to refine what we put here and make it more accurate. So we say here, Z star is the number that catches that word again, central probability C, under a standard normal curve. By standard normal curve, what we're mentioning is mu is 0, sigma equals 1. We just want to count standard deviations for any kind of normal curve. But it turns out you can just do it on the standard normal curve by calculating a z-score. So we'll go between negative z star, positive z star to give this full statement. Z here just means that uppercase Z is distributed normally with those parameter values mentioned. So completing the table here isn't really necessary. We can recalculate Z star pretty rapidly in RStudio. But think of this as just a way for us to practice calculating any Z star. The picture is very similar to what we did in the chapter 13 notes. We take a normal curve, This could be any normal curve whatsoever, but we're only doing it for one because you can just standardize to N01 and get the same exact values for Z star. So we go N01 here, implies the center is 0, and then we pick a level of confidence. In our derivation, we had approximately 95% confidence, but this could be any value. So let's put down a picture that goes like this. From here to here, in the middle, seem to have trouble drawing these in a symmetric way. Let me try once more. Maybe if I fudge that point, move it a little bit further to the right, it'll look slightly more believable. All right, imagine that's perfect symmetry there. In the central region, this is where we'll have confidence C, whatever that confidence level is stated to be. Then alpha on the tails, similar again to what we did in the prior chapter, this will be 1 minus C divided by 2 in area. This one would be 1 minus C divided by 2 as well. Off to the left is negative Z star, and there's no harm in calculating it. Negative Z star is just equally as good as positive Z star because it gets used both due to the plus and minus. So you really need both. We just typically report the positive value. It comes from right here, and the syntax would just be Q norm, 1 minus C divided by 2. Because the parameters we give it are 0, 1, we don't have to state anything further. Our studio is just going to default to the standard normal distribution. But if we want positive Z star, the last thing we want to put is lower dot tail equals false. So that will give us any critical value whatsoever. Let's calculate a few just to get a feel for how it goes. But any questions so far, folks, with where we're at on this stage? Okay, so really not too much syntax for this. And this is going to be very similar when we're in chapter 17. In chapter 17, we really must compute every critical number from scratch. So here, we'll go about just a C. That's a good one to start. State your confidence level. Let's fill out the table, and so we'll begin with 0.90 to start. Last thing you put in is Q norm. 1 minus confidence divided by 2, lower dot tail, set to false. And that's the whole story to this. This gives you your critical number right away. This is the explanation. The picture below informs us how the syntax should be written. So these pictures are always pretty valuable, but once you've got your syntax, we're all set. Run it once. The critical value for 90% confidence would be this figure here. With a lack of context, 4 decimal places is a standard amount to round to. So let's put this at 1.6449. Now, up the confidence to say 95% confidence. At a 95% confidence, we're saying that we're trying to capture an unknown parameter with a 95% confidence within an interval. The only way to make your confidence higher is your interval has to get wider now. And making your interval wider is expressed in multiple ways, but one of the ways is Z star gets wider. So there's a bit of a compromise here. The more confident you want to be, the wider your interval is. If it gets too wide, it's useless. In fact, if that's 100%, your confidence interval is the entire real number line, which is completely uninformative at that point. But at 95% confidence, we get the standard figure that you probably had in the back of your mind, 1.9600. This is rounding with carry. It's kind of annoying, but it's a standard value, so easy to memorize. 1.9600. Zero is there just to emphasize it's accurate, rounded down to the 4th decimal place. Then one last time, at 99% confidence, it jumps quite a bit now to 2.5758. So that's the computation we're using for getting your critical numbers out. Usually I just calculate these from scratch. And this is one of those times where you could come back here and look up the table. But because the syntax is so fast to type in, not a bad idea to just type it in from scratch. Kind of really just up to your judgment on that. It's a good idea to calculate for scratch, though, just as a good practice, because in chapter 17, like we mentioned, we would have to. But let's throw this in. That kind of went in weird. This is the whole syntax for getting our critical number in. Last thing we'll take a look at is the full procedure then. So if we want to write out the confidence interval in full, here's what it would look like. We just found how to get Z star. Sigma is an assumed to be known value. Again, that's pretty shady. I'll always mention that until we fix it in chapter 17. But X bar we will calculate, and we'll know the sample size n. So all quantities here are known. We can now start applying this into these kind of problems down below here. But this is kind of a longer problem. We have lots to do on this. We want to give a complete analysis to these data. If you like, you could take a look at it before we come back on next Tuesday's class. But I think this is probably a good stopping point for us today, so we don't have to break this problem in the middle. Well, any last questions at all then, folks, before we call it a night? Okay, when we come back on Tuesday, our goal is to take a look into running through the confidence interval procedure on these data. Then, this is a big concept question related to confidence intervals. Then we're going to get into hypothesis testing as well. And that's kind of the role of chapter 14, just introducing confidence intervals, hypothesis test, potentially for the first time, since statistics is not a prerequisite to this class. Then after we run through this, we'll do another one of those complete analyses, more concept checks, and then that's going to be it for chapter 14. I want to make one word of warning. As far as the reading goes, we know chapter 13 was pretty tough because it's abstract. Chapter 14 is not so bad. It's kind of the normal things we're doing in the class. But chapter 15 is really, really tricky. And it's not because it's abstract, it's because it has a lot of terms we have to get used to. We're going to look into significance levels, type 1 errors, type 2 errors, all sorts of interesting things that goes on in chapter 15. That's a good one to take a preview before we really get into it next week on Thursday. Seems was more likely. But I think that's all I have for folks. Have a great weekend, everyone. Have a great holiday as well. It's President's Day. And drive safe. I think it's still snowing out there. If you have any questions, I'm just hanging around here till the 7:30 class. So feel free to ask away and I'll be happy to help. Have a great weekend, folks.
I do have a question on assignment 4.
Yeah, absolutely. Let me take a look into that with you. Okay.
So I was looking at the part A of describe the unknown parameter, and it wasn't quite like anything we went over in the lecture notes, so I'm not exactly sure how to do that.
Yeah, this one is more similar to more of like the chapter 1 lecture notes when we're describing a parameter there. I would say for this one, let's see, young women aged 18 to 24 years have an average height. You wonder whether the mean height of female students at your university is different from the national average. So I'd say a good way to start on this one is the population would be women of this year, but they have to come from your university. So that's going to be the gist of the population on this one.
Okay.
Does that make sense for that?
So would it be the 78 students then?
Well, this would just be the sample size because it says to describe the parameter, it's going to be an unknown. And the
Oh,
sample X bar was the 63.1
mm-hmm.
inches. And this is tricky because this is the national value, 64.5 inches. That's not the mean mu either. Our mean mu just has to be described in full words. Does that help out with that one so far?
I'm sorry, I'm still confused.
Well, another way to think about this one is there's really two populations. There's everybody in the nation, And that's an approximate parameter value for that. But your population is different because, I mean, this is not literally you, but let's pretend you wonder whether the mean height of female students at your university is different. So now we're looking at a different population. We have mu is the population mean of
Mhm.
females of this age, but only at your university.
So then would the parameter be the ones at the university or would it be the national?
It would be the ones that everybody at that university. Well,
Oh,
every age range at that university.
okay, thank you.
Yep, absolutely. Questions over here? Oh, I got one for you as well. Here's this
Okay.
back.
Thank you, and I apologize for being a couple minutes late, the weather was.
Yeah, I know. No worries at all. I was expecting a slow start because of that.
Yeah. Had an excellent weekend, and, drive safely on the road.
Thank you. I definitely will. My tires are starting to get bald. This is not a great day for them.